The coherent state is an eigenstate of the annihilation operator and is a displaced harmonic oscillator state. Let we have an coherent state, and if we apply an operator, annihilation operator, then we can get the eigenvalue and the state as the coherent state as. So this is equation number first. We can write the coherent state as a linear combination of four states. This is important. We can write the coherent state as a linear combination of four states. For example, this we can write this as a linear combination because if we have 2 photon, 3 photon, 5 photon, 100 photon, and 1000 photon, this can be written in coherent as a linear combination of coherent state. So this coherent state can be written as a linear combination of four state. And now applying A to this state, this equation A, if we apply A, then we can get this A can be applied to this side and this side as well. And now if this is operating on n state, then we can get n under root and n minus 1. Now open this summation. For example, n is equal to 0, then C0, and here 0, then we can get 0. And if n is equal to 1, this is C1, this is 1, this is 0, this is a vacuum state. N minus 1, 1 minus 1. And n is equal to 2, C2, 2 under root, and this is 1, and so on. So this is a linear combination. This is a fork state, and we can write this fork state as a linear combination, and this is known as the coherent state. Further, if this A is applying to this state, and then we can get Cn plus 1 using this relation, then we can get Cn plus 1 because here n is equal to 0, then we can get C1 this, and this is 0. And if we if we put n is equal to 2, then C2, 2 under root, and so on. So this is this can be obtained from this linear combination. Now from equation 1 we can write equation 2 as this equation 2. We can write equation 2 as equation 1 means this is equation 1 and A this one, and summation Cn alpha n. It means that we can put the value of this equation 2 alpha, the value of alpha, then we can get this equation number 4. And from equation 3 and equation 4, we can get Cn plus 1 and n plus 1, which is equal to this. We have equation 3 and we have equation 4. So the left hand side are equal. Then we can write the right hand side are also equal. And from this we can get this relation. Now if n plus 1 is equal tends to n, then it means that n tends to n minus 1. And then this relation can be written as if n plus 1 is equal to n. So we have Cn and n plus 1 is equal to n and Cn minus 1 and alpha, and it means that Cn, this Cn can be written as alpha divided by n under root Cn minus 1. So this we can get. Now further, if we consider Cn, which is equal to alpha divided by n under root Cn minus 1, that already we have derived, and this equation can be written in this form, and this is a recursive relation because if we find this is Cn, which is equal to this, if we find Cn minus 1, then we can get alpha divided by n minus 1 Cn minus 2. Then if we find Cn minus 2, then we can get alpha divided by n minus 1 and Cn minus 3 and so on. And then finally we can get, this is decreasing, n minus 1, n minus 2, n minus 3, and this is equal to, this is decreasing and reach to 1, then this value c must reach to 0, because if we consider here, if this is n is equal to 1, then alpha divided by 1, and this n minus 1 c naught. So we can get this type, this term. And now Cn, which is equal to f, we write this in a compact form. This is equal to alpha n factorial. So this is C naught. So this is a compact form of this equation. Now equation 2 that we have already derived, equation 2, we have this relation alpha, this, and C naught, this must take the form as. Now to find C naught, we can determine by normalization. If we take the normalization of this, means if we apply alpha from right side, then this from this side and this from this side, so we have C naught this, and if we consider n is not equal to m, then n we have n factorial, and this is n, and if these are the same, m is equal to n, then it means that the C naught square n is equal to 0. If n is equal to n, then n alpha 2n, and if this m is n, then it means that n factorial square, so we have n factorial, and from this equation we can get C naught absolute square, which is this, and further we can write this equation n factorial alpha minus 2n. So this, and it should be noted that this term n is equal to 0, n factorial alpha minus 2n, this can be written in this form, because if you consider n is equal to 0, then alpha minus 0, and if n is equal to 1, this is alpha minus 2n. So this exponential and this term, this remains the same. You can try this by yourself. And further, C naught will be equal to e to the power minus alpha absolute square divided by 2. And now we have the value of C naught, putting the value of C naught in this equation, and then we can get alpha, which is equal to this, and finally alpha, we have this relation. We have this equation 5, and we also know that n, this n, we know about this Fock state, and this Fock state is, we know about the Fock state, and this Fock state is equal to n and n minus 1. So we know about this relation, and this relation can also be written in this form: a dagger divided by n, pick n, and n minus 1, and if we find n minus 1, then this is equal to a dagger divided by n minus 1, here n minus 2, and if we find n minus 2, this will be equal to a dagger n minus 2, and this is equal to a dagger divided by 1, and this is equal to 0 state. And for this, we have a dagger to the power n divided by n factorial and 0 state. So the Fock state can be written in this form. So this equation 5, putting the value of n in equation number 5, then we can get equation 5 implies that uh, alpha, this is equal to alpha. So alpha, which is equal to e to the power minus alpha absolute square divided by 2, summation n is equal to 0 to infinity, and putting the value of n and this, so we have alpha n already, n pictorial already we have, and a dagger n and the 0 state. It should be noted that summation of n is equal to 0 to infinity and alpha and a dagger की power n divided by n, and this is equal to so this is not n under root, but this is n pictorial. We have n pictorial here and n pictorial here, so we have n pictorial. So this is equal to e की power alpha a dagger and e की power minus alpha star a. So remember this, this term can be written in this form, in exponential form. This we have, and now this alpha, which is equal to e to the power minus alpha absolute square divided by 2, and from putting the value of this as e to the power alpha a dagger and e to the power minus alpha star a and 0th state. And here this term, this is a very important term, and this is known as d of alpha, and this is a displacement operator. Displacement operator. So the coherent state can be written as the displacement operator of vacuum state. And this relation shows that d of alpha, this equation shows that d of alpha operate on the vacuum state and transform into a coherent state. So it means that this operator is important. If this operator in a vacuum state, then we can get some more number of photons, and then if we have a more number of photons, then this is a coherent state. So this d alpha operator in a vacuum state, and then we can get a coherent state.